Good morning. So today we are on, if you look at your packet calendar, we are on day 6, and I'm going to be going over the notes of activity series and reaction rates with you. So as we go through this, make sure you have pages 11 and 12 out of your packet because we're going to be going through the notes together and you're going to be filling in the blanks. All right, so first of all, we'll talk about reaction rates. This whole unit has been about reactions, as you well know, and we've been talking about how to balance equations, how to classify different types of equations, and now you know how to predict products for equations. Well, now we're going to talk about the reactions themselves and different ways you can speed up those reactions. So starting off, reactions do not always occur at the same rate. Different reactions occur faster or slower than others. There are a lot of different factors that can determine how fast or slow a reaction can occur. So if we were to do some labs together, if you think back to a lab we actually did together, you put different metals in acid. So you put magnesium in acid, and then you put aluminum in acid. And you might remember that the magnesium reacted immediately with the acid, whereas the aluminum, it took it a little while before you saw a reaction happen. So that just shows you, just because you put two things together doesn't mean you're immediately going to see a reaction happen. Sometimes it takes a while. So what is the definition of reaction rate? It is a change in concentration of a reactant or product over time. So as a reaction takes place, you know that the reactants are on the left side of the equation, the products are on the right side. And something you haven't seen yet is when we put brackets around the reactants or products, we're talking about the concentration of each one. So over time, as a reaction takes place, you're going to see the concentration of the reactants decrease, and you're going to see the concentration of the products increase over time. Now, what are some different things that can affect reaction rate? Well, a lot of the things we're going to talk about also affect how quickly something dissolves. Now, keep in mind, dissolving is not a chemical reaction. So when you dissolve sugar in water, that is just a physical change. You are not performing a chemical reaction. But the same principles apply for speeding that up. So I'm going to be using that as my illustration today. If you were to make some sweet tea and you're trying to quickly dissolve the sugar in the water, what are some things you can do? Well, one of the first things that comes to mind is increasing the temperature. If we put that water over the stove and heat it up, then the sugar is going to dissolve more quickly. Another thing that you're going to want to do is stir it. Stirring is going to increase the rate at which that sugar dissolves. Some others that you might not think about immediately is increasing the concentration. Let me put that here since it's a bigger word. This is a bigger blank. So if you were to put the more solute, the more sugar you put, the more quickly you're going to see a reaction happen. Another one is surface area. So if we decrease the surface area of a solute, we're going to see it dissolve or react faster. So in other words, if you had a big block of sugar and tried to dissolve that in water versus a bunch of little tiny pieces of sugar, in this second example, there's more outside surface exposed to the surrounding solvent. So you're going to see that dissolve faster. Now keep in mind, once again, I'm talking about dissolving right now. reactions are chemical changes, but again, we're talking about factors that affect the rate at which these things happen, and there's a lot of overlap there. The last one I want to bring up is a catalyst, and this is probably a term that you may remember from biology. Catalysts speed up the rate of reactions by lowering the activation energy needed for that reaction to occur. But catalysts are kind of cool because they are not consumed by the reaction. All they do is come along, lower the activation energy, which speeds up the reaction, and then they go on to help someone else out with their reaction. All right, so now what we're going to do is go through each one of these and explain how each of these factors can speed up the rate of a reaction. And the first one we're going to talk about is stirring. By stirring two reactants together, you increase the frequency with which reactants would collide. So the whole impetus for causing a reaction to happen is you want the reactants to come into contact with one another. You want the reactants to collide so that they can react. So if you stir them together, you're forcing them to collide with one another, which is going to speed up the rate of that reaction. All right, the next one is surface area. And remember, surface area is increased by using a smaller particle size. This is the one that has its smaller particles, but more surface is exposed. So surface area is increased by using a smaller particle size. This also increases the frequency with which the reactants would collide. So now that more of their surface is exposed, the other reactants have more that they can touch and react with. All right, the third one is a catalyst. Catalysts are used to lower the activation energy for a reaction. So in other words, before a reaction can happen, so much energy has to be absorbed by the reactants. So what happens is a catalyst comes along, it lowers that activation energy. So now the reactants don't have to absorb as much and the reaction can happen faster. So by lowering the activation energy, a reaction requires less energy to start and therefore will begin sooner and complete faster. All right, the next one is temperature. By increasing the temperature, you are increasing the rate of reaction by simply adding energy. So remember, activation energy is how much energy those reactants have to absorb before the reaction can occur. So if you add energy by increasing the temperature, you're saving them some time. They don't have to acquire it themselves. And the last one is concentration. A greater concentration of reactants also increases the reaction rate by increasing the frequency with which the reactants collide. So if you have more in the beaker, more solute, more reactants, they are going to come into contact with one another more frequently. All right, one more thing about temperature. A reaction can be exothermic or endothermic. Exothermic means that heat is being released, or you can think of exo as exit. Heat is exiting the system. Endothermic, you can think heat is entering the system. So if you ever do an experiment and the test tube feels hot after the reaction has occurred, that means it's exothermic. And if you ever feel the test tube and it feels cooler, that means heat has been absorbed. So it's endothermic. All right, moving on to our diagrams at the bottom. These are called energy diagrams. And you can see what's happening here is we're showing what happens to the energy before and after a reaction occurs. So this would be the reactants. I'm going to put an R here at the beginning of our graph. Those are our reactants. Here at the top, this is where the reaction occurs. And then down at the bottom, these are our products. So same thing for our second diagram. The reactants are here. The products are here. Now notice, if the product's energy is ever less than the reactants, that means that more energy was released. More energy was released than was absorbed. So that is an exothermic reaction. Whenever the reactants end up being lower than the products, that means that more energy was released. But in this one, you see that the products end up with more energy than the reactants started with. So that means more energy was absorbed. So that would be an endothermic reaction. All right, so we're going to talk about each of these letters in the reaction coordinate diagram. The first one is A. A stands for the activation energy, the amount of energy to start a reaction. So notice your reactants start here. They have to gain this much energy before the reaction can occur. So that's represented by A, the activation energy. B is the potential energy of the reactants, the energy within the reactants. So the reactants don't start at zero. They don't start at zero energy. They start up here in this diagram, meaning they already had this much energy and they only had to gain a little bit more before the reaction could occur. You'll notice in our second diagram that these reactants started with less energy. So they had to gain a lot of energy before the reaction could occur. All right, we'll flip to the back now. But I'll keep going back to the front of this sheet and referencing those diagrams. So letter C is the heat of reaction, or the energy given off or absorbed during a reaction. In other words, it is the net amount gained or lost. Now, if you don't know what net means, I want you to think about your paycheck. So the amount of money you should be making without taxes would be your gross income. But of course, a big chunk of that amount comes out of your paycheck and goes towards taxes. So you are given a net amount of pay. So that's the same thing going on here in this reaction. You'll notice that this amount was absorbed, this amount was released. So from here to here, this amount absorbed, this amount released, that cancels out. So the net amount of energy, in this case, lost by the reaction, is from here to here, and that is C. If you look at the second diagram, this amount was gained, and this amount was lost. So from here to here, this cancels out. So the net amount, in this case, gained, is letter C, or the heat of reaction. All right, moving on to letter D, the activated complex. That represents the total energy of the entire system. So you'll notice that that is the arrow going from the bottom of the diagram all the way to the top of that hill. So the entire energy in the system is the activated complex. Letter E, the activation energy of the reverse reaction. The amount of energy required to start the reverse reaction is the activation energy of the reverse reaction. So if we started with the products and went in reverse, the amount of energy that the products would have to gain to go back to what they were is represented by E, the activation energy of the reverse reaction. And lastly, we have F. The potential energy of the products is the energy within the products. So just like the reactants start out with so much energy, the products end up with so much energy as well. So you'll notice for an exothermic reaction, the products have less energy than the reactants did. And for an endothermic reaction, the products have more energy than the reactants did. All right, we're going to skip this next little section here. You can just put an X through that. And we're going to move on to this diagram and do a few examples. So the first question is, what is the activation energy? A, B, or C? The answer would be A. This is where your reactants start. This is where your products end up. The reactants have to gain this much energy in order for the reaction to start. So that's A. What is the heat of reaction? Remember, that's the net amount of energy. So this much energy was gained, but that same amount was also lost. So the net amount lost in this reaction would be represented by C. And then lastly, what is the activation energy of the reverse reaction? If we want to go in reverse, we have to start at our products, go all the way to the top of the hill. So that's represented by B. All right, and then lastly, just a review of what a catalyst does. It says, we mentioned earlier that a catalyst could be used to speed up a reaction. This energy diagram represents how. So notice that there's a big hill, so a lot of energy that has to be gained before a reaction can occur, versus the catalyzed pathway, which is a lower hill. Not as much energy has to be absorbed. So it says, notice that on both pathways, there is a certain amount of activation energy needed. However, the catalyzed pathway has a lower activation energy than the uncatalyzed pathway. So that's normally represented by a dotted line when you see the catalyzed pathway. All right, I'm going to now show you a few examples. This is actually one of the worksheets that you've got to turn in to me by Monday night, but I'm going to go through it with you here just to make sure you understand. I would encourage you to try these on your own first, and then, so maybe pause the video here and then come back and watch it and you can see if you got these right. So looking at this diagram, you'll notice that we have actual numbers here to look at. So our reactants start right here. They start with 5 kilojoules. That's what Kj stands for. They start with 5 kilojoules of energy, and they end up with 30 kilojoules of energy after the reaction takes place. So the first question is this an exothermic or an endothermic reaction? Well, which one has more energy, the reactants or the products? The products had more energy. That means that more energy was absorbed than was released. So this is an endothermic reaction. All right, letter B, what is the PE stands for potential energy of the reactants? In other words, how much energy did your reactants start with? They started with 5 kilojoules. Letter C, what is the activation energy for the forward reaction? So if we want to go from reactants to products moving forward, how much energy do these reactants have to gain? Well, we have to do a little bit of math for this. If you look at the very bottom of our energy chart to the top, that's 40 kilojoules minus the amount they started with. So minus 5 gives us 35 kilojoules is the amount they had to gain. Letter D, what is the potential energy of the products? So the products, how much energy do they end up with? 30 kilojoules. Letter E, what is the activation energy for the reverse reaction? So if the products want to go back to their original form, how much energy do they have to gain? Again, we have to do a little bit of math. Take the entire complex, which is 40, subtract the amount they already had, which is 30, and you get 10 kilojoules. Letter F, what is the activated complex? So that's just the entire energy of the system. That would be 40. And then G, what is the heat of reaction? Remember, that's the net amount gained or lost. Well, if we look at how much they gained, remember that's the activation energy. So they gained 35. How much did they lose? They lost 10 of that. So if you take 35 and you subtract the 10 that they lost, you get 25. So 25 kilojoules is the heat of reaction for this equation.